Let's wait for 2 3 minutes. After that, I will start. Good evening. So last class, uh, I think you have asked me that extrinsic magnetic field. Uh, I was wrong about that. It was not Saturn actually. Saturn comes under the Earth type magnetism. That is, it has its own magnetism, intrinsic. Okay, so I forgot that. I think in week 10, I have mentioned somewhere. Just check the notes. I will show you. Let me see. I think one assignment question is there, right? Week 11. Think- Yeah. Uh, I forgot that. So that day was a mistake from my. Mhm. Say, good, good. Okay. So और एक चीज वो मीटिंग लिंक थोड़ा नोट कर लेना. I have given it in the chat box uh, because this will expire. My Google Meet has some problem right now. Hmm. It is actually UDZVEIN and QWB. VEIN, QWB. Hmm. Okay, let's start. So this is week 12. Actually, this is an extra session, but I will complete the week 12 here so that in the next session, next Tuesday, we will solve some numerical problems on the atmospheric physics. So I will jot down some numericals based on the assignment questions only, but changing a little bit so that it will be helpful for everyone uh, to solve numerical problems. So, so this is week 12, problem solving session on atmospheric physics. So mostly in this week 12, the solar wind acceleration will be covered. There's a long derivation, so we will do that. But what I think is that in the derivation which is made in the NPTEL lectures, there's some problem in it because the final expression I am not getting based on whatever the way it is being done. So I will make a change. So then we will have two different derivations. One is uh, by the NPTEL and one is whatever I will do. And we will see that which one is uh, the giving the correct expression and in the end. Okay, so this will do. But before that, let us just quickly go through the assignment 11. So assignment 11 was that a defined magnetic field of a planet represents. So this I have already written these 3 points. Whenever a planet or any object, what we call, it has a liquid core. For example, in our planet Earth, it has the outer core is fluid, so it has a liquid kind of a core, and the core is rich in metal. As you know, in case of Earth, I discussed in the last section that the outer core of the Earth is fluidic in nature and also has good amount of charged particles which comes from nickel and iron, Ni and Fe. Okay. And the third one is high rotation rate. Earth rotates pretty well, so it's 24 hours. So these three conditions all should be satisfied. Then only you will get a defined magnetic field. So this is already been discussed. So this is all of the above is correct. Second is Venus does not have an intrinsic magnetic field because its rotation rate is very, very low. Okay, it has a molten layer. It, but the major reason why it does not have its own magnetic field is because of the rotation rate. Okay. Next is during geomagnetic storms. We will discuss a little bit about the geomagnetic storm today. So during geomagnetic storms, you can understand that geomagnetic storms is somewhere related to the sun's activity, the solar activity. So when the solar activity is stronger, we know that in general, let me come here. So third one, we know in general, suppose this is your Earth and this is your this axis, and the magnetic field gets compressed in the day side, right? And it expands, elongates like this on the other side, right? So this is the day side. So what happens is that the effect of the sun is observed here, right, in the day side. So the day side is always being compressed. But when you have a geomagnetic storm, which is mostly due to the solar activity, peak solar activity, that results into further compression of this magnetic field lines. Okay, so if you now see the options, magnetopause distance on the day side decreases. Of course, whenever you have a strong solar wind or geomagnetic storm, what we say. We will discuss about geomagnetic storm a little bit today. So at that time, what happens is that this magnetopause distance on the day side, it tends to decrease because the magnetic field lines will be compressed towards the surface of the Earth. Okay, so this is one of the things. Plasma beta parameter I had discussed in the last session, uh, but it is not. I couldn't find much of the plasma beta parameter, but it is an important factor in deciding the magnetopause distance. We have seen in the last question that how the magnetopause distance is calculated. So in some way, it is the balance actually between the your solar wind which is there and magnetopause happens when there is an intrinsic magnetic field. In case of induced magnetic field, you have your ionopause. Whereas in case of intrinsic magnetic field, we have seen the magnetopause distance. So plasma beta parameter is an important factor in deciding the magnetopause distance. So A and C are the correct option. It is not constant. Okay, fine. Next is the angle of the sun's radial magnetic field does not depend on. So we have discussed this. Dr, it does not depend on the magnetic field itself, but it depends on the latitude because it depends on the rotation. So sun's rotation is not constant everywhere. It's not a rigid body rotation. So it depends on the distance, it depends on the solar wind speed, and it depends on the latitude. Okay, but it does not depend on the magnitude of the magnetic field. We have discussed it. Okay, so I'm not going into the details. The next question, again about geomagnetic storm, but this question is a bit research oriented question. So I also don't have much idea about this geomagnetic storm. So really, if you find it by Google search and try to understand what it is, so I could find that the second option is much more close, that this disturbance time index. So one of the index of calculating the geomagnetic storm is DST, the disturbance storm time index. The northward component of interplanetary magnetic field has a good linear variability, a linear relationship. Okay, so it shows the good positive correlation with the disturbance storm index and the interplanetary magnetic field. So much details I cannot give here because I don't have much idea about the research. So you have to go ahead and just give some time and try to understand this. Sixth is the moon of the earth does not have an intrinsic magnetic field because it does not have any core. First of all, it does not have any atmosphere. That is one of the reasons. It does not have any atmosphere and it does not have a molten core. So that is the major part. What else? The static model of corona. We have discussed the static model of corona the last session, and we found that the pressure we observe in the interstellar pressure we observe is actually much lower than the computed pressure based on the static model of corona. So just a point to make. This is I think the first one. So the P interstellar pressure, which is observed, okay, the observed pressure is roughly about 10 to the power minus 15 hectopascals. Or let me see. Oh, sorry, Pascal. Okay, but through the static model of corona, we have derived the expression. It comes out to be about 10 to the power minus 5%. So you can see that the static model of corona is giving a pressure which is much higher than that of the actual pressure. But in general, what it should be, because interstellar distance is too large, so R is tending to infinity. It's very large distance. So at practically very large distances, you would expect that the pressure to be much lower, which is observed. Okay, but it is not such. Okay, so that's why the model fails, because it does not predict the actual observed solar wind pressure near the Earth or whatever the distance, higher distance. Okay, so this is the last and the last one, which I have made a mistake in the last session, that extrinsic magnetic field. Saturn does not have extrinsic magnetic field; it has its own magnetic field. Okay, Venus and Mars, they do not have the intrinsic magnetic field. Therefore, these are actually extrinsic, the Venus and Mars. But Saturn is Earth type magnetic field. Okay, so just a clarification. Okay, so yeah, these are the couple of things. I will not go into much details of these questions. These are based on whatever is being covered. Okay, so now I think we can just move into this the week 12 content and finish the all the week's content therefore. And once it is done, then we can solve numericals in the next session. I will prepare some good amount of numericals and we will solve each and everything. Okay. So what we were discussing in the last session at the very end was the Parker's theory of solar wind acceleration. So we will start with whatever is being covered in the NPTEL lectures, just for a revision kind of a thing. And uh, once it is done, once we move further into it, I will make a change, and that change will ultimately give you the final expression. Okay, so just look into the actual lecture notes which the NPTEL is providing and this one. You will find that the expression which I will come to will be same as the expression which the NPTEL has given, but there is a problem in the derivation somewhere. Some factor is uh, is creating that problem. So I will come to that. Okay, okay. Just let me go one step behind and come to the week 11 and go to the last part. Just quickly discussing about the assumptions of the solar wind theory. Okay, so these are the couple of things which we have discussed at the very end. Just a quick 2 minute recap of whatever we have done. Then we will start the derivation. So Ian Parker, 1958, has given this particular theory. First thing which we are talking about here is the processes that enable the solar wind to escape the sun's gravity. Because mass of the sun is huge, 3 into 10 to the power 6, 26 kg. So if the sun's mass is huge, then the gravity will be very strong. Then how the solar wind is escaping? That is the first question. And not only the solar wind is escaping, but the solar wind is having a supersonic speed. Okay, so that is very important. So how the solar wind is escaping the sun's gravity? So people have seen that based on laboratory experiments or some observations, they have shown that the heating inside the sun and strong pressure which is present within the sun, that means a compression kind of a thing because there is a very strong pressure there. Okay, so because of heating and strong pressure, plasma get a huge amount of energy. Okay, and problem is that once you leave the sun, the pressure immediately drops down and it drops very rapidly. This decrease in pressure will result into an expansion. We know that pressure decrease result into a volume increase and with a constant temperature definitely, but here the temperature changes altogether. Fine. So after that, there is an expansion. Okay. So because of this pressure gradient, high pressure over near the sun, and as you go, say 1 astronomical unit near the Earth, the pressure decreases rapidly. This pressure gradient results into the solar wind to leave and accelerate. So solar wind is leaving the sun's gravity because of the heating and the compression effect, and it is accelerating because of this pressure gradient. Okay, so majorly the sun's gravity is playing an important role and the pressure gradient is playing an important role. Of course, electromagnetic part will also come. So these are the couple of things, magnetic, electric and electromagnetic, but these are very negligible compared to the pressure gradient, the force or acceleration and the what you call as the sun's gravity. Okay. Now, couple of assumptions before going to the derivation. So we have considered that the solar wind can be treated as an ideal gas. Flow is radially away from the sun. Okay, this is also fine. Acceleration due to EM fields, they are small and can be neglected. You will see that. And solution is time stationary, which is one of the assumptions. So what physical processes we will be using is this: conservation of mass, momentum, and heat. So essentially the continuity equation first, then the momentum equation and the heat conservation. So these are the couple of equations which we will be using. Heat conservation means something related to the ideal gas equation. Okay. And finally, you will have the this comes under magnetohydrodynamics, but we don't need to go into much details of that. Okay, couple of other things. Plasma is assumed to be a single fluid. No difference between electrons and ions; they are same. And frequent collisions and strong external magnetic field can create large number of electrons or ions. So these are the couple of assumptions before going into the derivation of the solar wind acceleration. Okay, so this we have discussed. Now we can start the things. Okay. So, as we have discussed, conservation of mass and momentum is are the two things which we will be mostly using. And then we will use the heat conservation, that is the ideal case. Okay. So, let's write it down. Delta rho delta T plus del dot rho U. Just watch the derivation. You already have one of the derivations which is there in the lecture notes, and this you will always get. So Just step by step follow it and let me know if there is a problem here. Okay, so this is the continuity. This is no equation. Okay, we have discussed it for the atmospheric physics also, continuity equation. Next is the momentum equation. So this is how the momentum equation can be written. This is the nonlinear term of the momentum equation. Okay, if rho is being introduced here, and hence we are writing minus grad T. The pressure gradient we have discussed, and plus the electromagnetic term J cross B. I'll come to it. B you can understand is the magnetic field, and you have rho Fg, the gravity. Okay, so you have the gravity of the sun. This is the pressure gradient force, and this is the electromagnetic force. Is the electromagnetic. Here, the J is the current density. This is the microscopic Ohm's law kind of a thing, and this is E plus. You can write U cross B kind of a thing. Okay. Some way the Lorentz force and the charge density and all those things are combined. Okay. This is the current density. Okay. And as you can see, what we have written in the when we were talking about the fluid flow in the atmospheric physics, the lower troposphere, there what we have seen is that we have written minus grad P by rho. But here the rho is multiplied altogether. So that is the second one. So this is the momentum equation. All right. This is the momentum equation. Okay. Next one, we will use the steady state, steady state flow assumption. So using steady state flow assumption, what will happen? The time tendency term, that is del T of rho, that will be zero. Okay, so therefore we will get del dot rho u will be equal to zero. This is the mass flux. This is mass flux. Which month? This is the solar plasma. Okay, the mass flux. This is all related to the sun or solar wind. Okay, therefore now what you have from the momentum equation, we get this term is zero now because we have the steady state flow assumption. So you have now rho u dot grad u is equal to minus grad p plus j cross p plus rho h. Okay. Now comes the ideal gas law. P is equal to rho r T naught. T naught is sun's photosphere temperature, means sun's surface temperature, let's say 6000 Kelvin. Okay. And we also assume, which we have already written earlier, that is assume spherical symmetry. That is only the radial component we will be using. Purely radial component. So U will be assumed that it will be UR R hat. That is only in the radial component. So purely radial, which we will be considering. This is one of the assumptions we have written. Okay, what is the gravity? H. You can write this. This is minus G M. This is the mass of the sun divided by r square. This is mass of sun. Okay, so these are a couple of things. Okay, one thing I have forgot to mention is rho is the density of the plasma, the solar wind, because solar wind consists of plasma. Okay, these are a couple of things. Okay, what about grad P? Simple, because we are talking about the radial component, so we will be writing dp dr. Alright. Why not delta P delta? Because we are only considering the radial component. All other components are assumed to be zero. That's why. Fine. All explanations are clear now. Rho u dot grad u is minus delta P. Oh, again, I'm writing delta P, but You should write dpdr minus rho g m by r square plus j cross b. This term, we have already told that electromagnetic term is, we will be neglecting that. So this is 0. This is smaller compared to other terms. So you can understand the acceleration of the solar wind or the plasma from the sun is somewhere dependent on the gravity. You have to escape the gravity first, and it depends on the pressure gradient from the sun outside the sun. What is the difference in the gradient pressure? So those two will ultimately result into the solar wind acceleration. Okay, so okay, this is fine. What else? Okay, from the continuity, from the continuity equation, what we have? Steady state continuity. So it is del dot rho u is equal to 0. This is what it is. Now divergence only in radial component becomes 1 by r square del del r square rho u. I am not writing now this vector. It's just understood now. Okay. It should be equal to 0. That means what? This means that r square rho u is some constant. Okay. What we will do is that we multiply with a 4 pi. This is just to make the expression better. So this is some constant. This is an important expression which we might be using. This is A, let us say. And next is we assume again that a hydrostatic balance. Okay, we assume hydrostatic balance. Why? To get the pressure gradient. Okay, so minus dpdr is equal to rho gm by r. This is fine. You know, we have seen that dpdz in case of our atmosphere it was minus rho g. And this is what I'm writing for the sun. G is G, mass of the sun divided by R square. This is the rho. Negative sign I have taken on the other side. And dp dr. dz is replaced by dr. Okay, this is okay. And next what we will do is that, let's say, it is right, rho u delta u delta r, r hat will be equal to 0. Okay. Why we are writing this? U delta because of this. See, after neglecting, let me I have skipped one step. So it will be what? Rho u. There's a graph. So only radial component we are taking. So this. Okay. And this is r hat, which is equal to minus dpdr r hat minus rho gm by r square. R hat. Perfect. This is the equation which we will get. Okay. So from this equation, we are writing this. Why? Because these two are equal. Because the pressure gradient is balancing the Hg according to the hydrostatic balance. So let's say this is some 1, let's say. So from 1. Okay. So this is what we have got. So what we get here, the radial distance u is actually constant. Okay, the radial distance u is actually constant, but it must accelerate. That is the point. It must accelerate. So we have to see now further. Now, what they are making this assumption is that the plasma is the same fluid, so PE is equal to TI is always equal to temperature. It's the same temperature, and the density is actually N into K. K is the Boltzmann constant. You have PE plus TI which is 2n kb. I have a problem here. I think this is creating a trouble later on. We will see that because since the plasma uh, is assumed to be a continuous fluid, you should have written this rho as mkBp. That's all. There should not be a two factor here. So I am a little bit worried about this. And I am sure that because of this, we will not get the correct expression. I will show you. Okay. But right now, let us keep this and try to see. So rho is equal to n into m. Why? Why n into m? What is n? It is the number density of the charged particles which are present. So number density is nothing but the number of charged particles divided by volume. And if this is the mass of the plasma or charged particles, so n times m by v is nothing but the density. So this is fine. Okay. Now the pressure is, you know that it is your rho into kT. Okay. So rho can be written as I'm sorry, this is fine. Rho RT actually, K by L. Yeah. Okay. So now what happens is that we can write this as, instead of rho, it can be written as 2 rho KT by M. Now how can we write it like this? Based on these two. Okay. Based on these two, we can write the pressure as this. And also we are using, let me see. Yes, I think this is the thing. EV is equal to LRT, and so this is N. Okay, so P is equal to NRT, which is now this will be now 2 times that R can be written as kb by M into T, and in that sense you have your N is equal to actually rho by M. I think this I'm making something. Yeah, this will be rho by N into kbt, and this N is actually assumed as this. So n will be equal to really the 2n because ne and n are equal. So it will be 2 rho by m. The last session also we have discussed this. So this is what you get. Okay. Next, you have dpdr, which is equal to minus rho gm divided by r square. This is your hydrostatic approximation. Now, can we write rho from here as m into T divided by 2 kg? So just replace that mp divided by 2 kg into gm by r square. This is your dptr. And remember, this small m which we have written is the mass of the plasma of the solar wind. Next is very simple. You just have to do some integration. So dp by t is nothing but minus m divided by 2 kg gm by r square and dr. That's all. You just integrate it, and let me just write the expression. It will be log p is equal to m g capital M, that is the mass of the sun, divided by 2 kT dr by r square. So dr by r square will be 1 by r. Alright, plus some constant. This is what you get when you integrate it without any limits. Because that's why the constant comes. Now we will put some limits at p is equal to p naught, that is r is equal to capital R. I think this is not the way I should write. At r is equal to capital R. What is capital R? Is the radius of the sun. Okay, at R is equal to capital R, that is the radius of the sun or the surface of the sun. P is, let's say, equal to P naught. Then what we will get, log of P naught, because this should satisfy this criteria. So mg capital M divided by 2kt capital R plus k. So this will give you what is the value of k. Alright, this is what you do. Just put that in the main expression and you will get it. So log of p, well, what? Yeah, log of p is equal to mgm divided by 2kt r plus. There is a k. This k I will write here. So log p naught minus mgm divided by 2kt. So log p minus log p naught. Step by step, let us go. And these are all common. We can take 2kt. That's all. 1 by r minus 1 by delta. And so what you will get is that this is log p by p naught, that is equal to mgm divided by 2kt 1 by r minus 1 by capital R. Fine, this is all, these are all okay. These are simple steps of integration. What the final expression will be? P is equal to P naught. You can understand this will be an exponential function. And you have mgm divided by 2kt 1 by r minus 1 by capital R. This is what you get. This is, let's say, some expression. Okay, the pressure is following an exponential function. Now, if R is much greater than capital R, let's say, then 1 by R should be much less than 1 by capital R. Just the inverse, right? So, if that is true, if 1 by R is less than 1 by capital R, then this expression should be negative. Therefore, P, the pressure, should decrease, which is perfect. As the R increases, the pressure should decrease. So, the expression shows that the P of R is exponentially decreasing. Exponentially decreasing. Away from the. That's good. Let's go further. So suppose you have a sun. This is your radius of the sun. And this is some height h. Height from the surface. This is h. So h, and if suppose here this one is the total distance, which is capital small r. So this can be written as r minus capital O. The total r minus the radius of the sun is the height from the surface. Okay, so this is actually distance away from the surface. Okay, so what you get here is that 1 by r is equal to 1 upon h plus r. This r is this from the center, which is equal to, can be written as, r can be taken outside and can be written as the. This we generally do. Remember when we do in physics the gravity, how the gravity changes with height. Okay, so now 1 by r as it is, can I write it like this? This is just a step of binomial expansion, neglecting higher order terms. Okay, so what we can finally get is 1 by small r is 1 by capital R into 1 minus h by r. That's all. All right. Now, let's. So this will hold only when h is much less than. For this case, let's see how my pressure changes. So P naught, we have got this expression. mg capital M divided by 2kt 1 by r 1 minus h by r minus 1 by r. This was the expression. This was 1 by r, and this is what we have written after the expansion. Okay, okay, let's go further. So it will be p naught exponential of same mg m by 2kt. Let's solve the inner bracket, this one. So it will be 1 by r minus h by r square minus 1 by r. Right. So 1 by r, 1 by r cancels. So what you get? E is equal to p naught exponential. You get minus mg capital M divided by 2kt h by r square. Okay. This is what the expression you get. Right? This is the expression you get. Now, what we do is that we write lambda, some lambda is 2kt divided by mg m and r square. So ultimately writing this one with an opposite, means inverting that. Okay, so inverted. I'm writing that as lambda. Now this gm divided by the surface, the radius of the earth square, radius of the sun square, will give you the gravity of the sun, right? This is fine. So lambda becomes equal to 2kt by g of sun. This we can define as the scale height. Just we have defined it for the atmosphere. Therefore, P will be equal to P naught exponential of minus h divided by lambda. Okay. Now, what happens is that when R is much greater than capital R, then your P becomes equal to P naught. This is when R is much less than, I mean, R is close to R. Then what will happen? Okay. Now, here when R is much greater than capital R, P naught exponential. Just look at the expression P. So what you get? This. So as R is large, 1 by R tends to 0, and hence we are getting this. So come to this expression here. So 1 by R is tending to 0, so you are getting something like this, right? What you can say from this expression? P naught exponential mg capital M divided by 2kt, the negative sign. Look, this expression is constant. So pressure at larger distance is constant, is becoming constant. Problem is this. This is not right. This is not correct. Because at large distances also, solar wind accelerates. Okay? It can't be taken as constant. If P is constant, then delta P is 0. So there is no acceleration. Okay? So the problem is that what can be the possible problem is that your U is equal to UR, that is the symmetric approximation, is not correct. This is one of the possibilities. And number two, the hydrostatic approximation cannot be taken. Can't be considered. Because of these two assumptions which we have made, we are getting a thing that at very large distances, the pressure is becoming constant. So there is no acceleration in solar wind. But observation shows that there is a good acceleration. So there is some problem. And the problem is because of these two assumptions. Okay. The next, we will try to improve this. The Parker's theory is now will be improved. Okay. So we will start again. So now improvement, that is without taking these two things. Okay. Is that you start with rho u du dr is equal to minus dp dr minus g rho gm by r square. So first of all, u is equal to ur is not correct. See, we are still taking u as a function of r. So I don't think this is one of the possible thing. So I just cancel this. Only the hydrostatic approximation can be considered. Let's see later what we can get from this. We are still taking u as a function of r. That's all. Okay. And this is the final expression because electromagnetic term we have reduced. And we have also got an expression like this. Rho u is equal to constant, right? This is what does this mean? This is the flux coming out is constant. This is the flux because rho into u is there. The plasma flux, mass of plasma which is coming. Now rho is okay. Let me write it properly. The pressure let's say, is equal to rho kt by m. This we can write because P is equal to rho RT. So just rho KT by M. Okay. And your rho therefore can be written as MP by KT. Okay. And also we have defined rho is equal to N into M. This is by the definition of the density. Perfect. So M is a P can be written as N into KB into this K and KB as well. Okay. So number density into Boltzmann constant into temperature. So here, what will happen is that in your NPTEL lecture notes or videos, you will find that this rho is taken as MP divided by 2 kg. This is because your number density is number of electrons plus number of ions, which are both same, almost similar. So that's why it is taken as 2N. And that's why the 2 comes. Okay. But I'm not considering that because we have already assumed plasma as a single fluid. There is no distinguishing of electrons and ions or plasma ions. Right? So if we take it as a single fluid, N is the density of the plasma, and hence we cannot write this. We are not writing N is equal to 2N. Okay. So just read the whatever they have and try to solve for whatever the final expression they are getting and whatever the final expression I am getting based on this. Okay, let's see. Okay, fine. I will go ahead with this. You can also try with P is equal to 2N kBT. Okay, you can also try. Just check whether to this expression, which is there in already in the NPTEL, you will get the final expression or not. Okay, I am not getting it. I was not getting it. So that's why I have changed to this. Okay, let's go ahead then. Okay, so dpdr therefore will be kt dndr. Fine. And finally, we get rho u dudr is equal to what was that? dpdr was there. So minus kt dndr minus rho gm divided by r. Perfect. So u dudr will be equal to minus kt Okay, divided by n into m, because rho is n into m, dn dr minus gm by r. So I have divided it with rho. Okay, this is the expression we are getting. Okay, let's just look into this expression. The only difference with if you take P is equal to 2 nkt will be that there is a 2 expression which will be present here. But I am taking it as a single fluid, so P is equal to nkt. Okay, and trying to solve it. Fine. So now let's proceed. We have already seen that 4 pi r squared rho u is constant. I am writing that as h, and rho is equal to nm. We have seen 4 pi r square nm u is, can we write n therefore constant f divided by 4 pi r square mu? Yes, you can write. And let's say dn by dr. Let's do it. So what we will get if we have dn by dr, then so differentiating n with respect to r, let me start it a little clear. dn by dr will be equal to f divided by 4 pi m. So I think by 9 minutes, it will the session will end. You have to join with the new link. Okay. Okay. So f by 4 pi m minus 1 by u 2 divided by r cube minus 1 by r square u square du dr. This is fine. There is nothing to be changed here. Now, instead of d and dr, let us write 1 by n d and dr. So 1 by n, 1 by n can be written as therefore this 4 pi r square mu divided by n. So let us write 4 pi r square mu divided by f into f divided by 4 pi n into whatever there in the bracket. So minus 2 u r cube minus 1 by r square u square du dr. Perfect. This is okay. What are the things which will be cancelled? 4 pi m f will be cancelled. Okay. So what you get is that r square into u will be multiplied. So it will be minus 2 by r minus 1 by u du dr. This is what you will get as the expression of 1 by a d and dr. This is perfect. This is matching with whatever is there in the lecture notes in the NPTEL. This is matching. Okay. Now let's say, okay, yeah, let's say this is your A. Let and this is your suppose B. Put B in. So what you will do? U du dr on the left hand side. Okay, and right hand side you have C minus kt by m 1 by n dn dr. So that's what I will write. So minus kt by m 1 by n dn dr can be written like this: minus 2 by r minus 1 by u du dr. Done. And minus gm by r square. That's all. This was the expression A. Just 1 by n dn dr is replaced, and you get this. Okay. Now further you can write the u du dr, just opening the expressions, minus kt by m. Oh, okay. Okay, so it will be 2 kT by mr plus kT by um du dr minus gm by r square. The only thing is that only difference is that in the NPTEL lecture notes it will be 4, this will be 2 because we have taken 2 km by 2, but here it will be like this. All right, this is done. Next, what we can do? Du dr term can be separated. So u minus kT by um du dr, and you have 2 kT by mr minus gm by r. That's so. This is our an important expression. Okay. So yes, this is an important expression. And what else you can do is that 1 by u you can take common, and you have u squared minus kt by m, because 1 by u you have taken common, du dr is equal to 2 kt by mr minus gm by r. So this expression is uh, the final expression of this derivation. We will now see that how these expressions can lead to several solutions and try to look for the final expression of the what you call as the solar wind acceleration. Okay, which will be a transcendental equation. So we will see that. So how much time is left here? Okay, it will end so maybe. Fine. Let's see here. One thing is that your this is about 1 by r, and this is about 1 by r square. So what happens is that this is actually decreases faster. Okay, decreases faster. So this is one of the important points. So at larger distances, this will decrease faster, but this will be slower. So it's making it a positive kind of a thing. So you can see that UR increases as R increases, because the term dominated by Gm by R square will be smaller. So this is one of the points. And what else? Yes, these are the couple of things. And so just give me a moment. So if it closes by then, just try the new link. Okay, there in the chat box also, and I have also mentioned. And I think near the surface, this GM by R square will be much, much larger. So it becomes, this expression becomes some way in negative. The RHS become negative. So we will see each and everything. Uh, Let me see whether it ends or not. We will join with the new link. Okay. Okay, let us start. So this is where we are. So near the surface of the sun, that is base of the corona. So T of corona is roughly of the order of 10 to the power 6 Kelvin, and mass is mass of the plasma, and capital M is M naught, which is mass of sun. So these are already been defined. The plasma mass. Okay. So near the surface, it is that your 2 kT by mr is much less than gm by r square, because r is small. Okay. So as r is smaller, this term will dominate, and because so gravity of the sun dominates. Okay. So this is one of the important things. So it is actually showing that gravity, sun's gravity is holding the corona or the solar plasma, whatever it is, the winds. Okay, let us now define a critical distance. Okay, so it's a critical distance at which this 2 kT by mr becomes equal to gm by r square. So there are 3 points. One is when r is less than rc. Second is when r is equal to rc, which is the critical distance. Third is r greater than rc. So these are the three different points. So at r less than rc, we have already seen this. 2 kT upon mr is less than gm by r square. Gravity dominates, and the right hand side is negative. Okay, here the gravity, sun gravity dominates. Okay, next r is equal to r3, so you get 2 kT by m. R becomes now rc, so becomes gm by rc square. RHS becomes 0, right? And finally, when R is larger than rc, you get 2 kT by mr is greater than gm by r square. Here, this term dominates. Okay, so the thermodynamical part or the temperature part dominates. Okay, now coming to this expression at the critical value, that is at r is equal to rc, then what is the value of rc? Therefore, so it will be 2 kT divided by mrc is actually gm divided by rc square. So can we remove one? Yes. So rc therefore becomes gm divided by 2k, and yeah, gm m divided by 2kt. This is yeah, gmm divided by 2kt. Okay. Now we define an isothermal, that is at constant temperature, speed of sound. We know that isothermal speed of sound, the s is equal to root over e by rho, which in case of adiabatic becomes gamma p by rho, right? So this is isothermal, that's why it is root over T by rho. This is simple expression you can easily get. And thermodynamically, we can write it as rho kT by m. Yes, P is equal to rho T by m into T. So rho cancels, it becomes root over kT by m. So CS, the isothermal speed of sound is this. So RC therefore becomes Gm by 2 Cs square. Why? Because Cs square is kT by m. Fine. So the critical distance, that is Gm upon 2 Cs square, is the distance where the role of gravity and the role of the 2kT by mr, that part becomes equal. Okay. The 2kT by mr is actually coming from the pressure gradient part. Part of it is coming from the pressure gradient. So pressure gradient is playing a role at larger distances, and at smaller distances it is dominated by the gravity. Okay. So these are the couple of things. Okay. So we have defined most of the things. Now comes is that at critical distance, same, we are dealing with the same thing. So at critical distance, that is R is equal to RC, you are getting 1 by U du dr into U square minus KT by M U. No, I let me see. So KT by M only. No U is there. This is equal to 0 because the right hand side is 0. This is equal to this. Okay, so we are getting this. Therefore, du dr at R is equal to RC can be 0. So if you either assume this is equal to 0 or you assume that U square minus, no, or if du dr at R is equal to RC is equal to 0, then this can be three things, either positive or 0 or negative. Okay. So if we consider that du dr is equal to 0 at R is equal to RC, then U square minus KT by M can be any of the three things. So there are a couple of cases. Okay, let's say R is less than RC. Okay, at R less than RC, which is well within the vicinity of the sun, so gravity will dominate. So 1 by U du dr and U square minus KT by M, what will happen? This will be less than 0 because gravity's effect dominates, right? So let's say this is negative. Okay, let us consider. If this is negative, then du by dr has to be positive. That means U increases with R. Perfect. So this is showing that there is some kind of an acceleration visible here. Okay, but if let's say R is greater than RC, then what will happen? Same expression if you write dr U square minus KT by M is greater than 0, right? Because at larger distances we have seen that the term which is related to somewhat pressure gradient is dominating. So if it is this, and let us say that this is still negative, let us say, so in both the cases, whether it is R greater than RC or R less than RC, we have taken that U square minus KT by N is negative. Then this has to be negative. Therefore, du dr is less than 0. So UR decreases with R. This is also showing an acceleration, but it is a deceleration kind of thing. Okay, this is what we are getting. There are other expressions, okay, where, so this is, let's say, some case one, where we have always taken this as negative. Next is case two, where the same expression, that is r less than or c, we will take. So 1 by u du dr u square minus kt by s, r less than or c will be less than 0, gravity will dominate. And now we will say that, let us say this term is positive. Earlier, both the cases we have taken negative. Now it is positive. If this is positive, this has to be negative. So du dr is less than 0. So u decreases as r increases. And similarly, r greater than rc. So there are many possible cases. You can understand du dr, and you have u square minus kt by u, which is greater than 0. So this now is still positive. This has to be positive. Therefore, du dr is greater than 0. So there are many cases which you can clearly see. Now, let us come back to, let's say, this expression. Okay, let's say this is uh, let's say D equation. So coming to equation D now. Okay, coming to equation D, let us write the equation first. So it will be du dr. Can I write it like this? So u minus cs, sorry, write cs, this, because 1 by u was there, so I have just multiplied it. This becomes equal to 2 kt by mr minus gm by r square. This was the expression, right? So now I know that cs square is kt by m. That is isothermal period of sound square, right? So can we replace a couple of things? So du dr u minus cs square by u is equal to 2 kt by n. What I do is that I multiply by r in the numerator and in the denominator. And in the second case, while r square is there, I multiply by a 2cs square and divided by 2cs square. So what you get? Du dr u minus cs square by u. This will be 2 kt r divided by mr square. And this, look at this. I will change the color. Gm divided by 2cs square. What is that? Rc, right? So this will be Rc into 2 into cs square divided by r square. And of course, this also is cs square. So let me write it once again. So du dr u minus cs square by u is 2 cs square by r divided by r square minus 2 cs square rc divided by r square. So finally, this is the expression which we will be getting. So u minus cs square by u, right, is equal to, can I take 2 cs square by r square common, and you get r minus. So if you don't take, so if we don't take that your p is equal to your rho kt by m, then you will not get this. we won't get this expression. Okay, so if you take, so in the NPTEL lectures, I have seen that P is equal to, it is written as 2 rho KT value. But this will give you du dr, the final expression is u minus 2cs square by u, which is equal to 2cs square by r square. You will get this, but you will get this, which is not the right expression. So just the final expression becomes this, which is not right, which is not same as this. Okay. So this is the final expression. So this is the final expression, which will be integrated later on. This is okay. The most important point is that at r is equal to rc, what you get? U becomes equal to cs, which is very important. Speed of sound, the isothermal speed of sound. U becomes the solar wind speed becomes isothermal speed of sound. Okay, so solar wind speed. So I'll just make a star mark here. Okay, solar wind speed becomes equal to cs when r becomes equal to the critical distance. Perfect. Now what we can do is that we can integrate both sides, both expressions, and what you get is this u minus cs square by u du, which is equal to 2 cs square by r square, r minus rc. Yeah. So what you will get from this result is that this 2 log u by cs is equal to 4 log r by rc plus 4rc by r plus constancy. So this is the transcendental equation, and has graphical solution. Okay, so couple of points just quickly I mention. One is that plasma starts at the surface of the sun, solar surface, with smaller velocity that increases towards the critical point. Okay, so at critical point, the speed varies, or speed, I would say, it reaches the cs, the sound of speed, sorry, the speed of sound, and then at r greater than rc, it becomes supersonic. Okay, so this is what it. So the final expression, these are the couple of, and you get a graph which is something like this. So you have this axis is r by rc, and this axis is u by p, and this is the value 1, which is u is equal to c. Okay, these are the, now there are a couple of lines you will find. Okay, the first one is, okay, so this is also one. The first one is like this. Okay, this is the number one. Okay, these are the couple of solutions. There are six possible solutions. The second one is something like this. This is the second one. Fine. The third one is like this. Okay, this is the third one. The fourth one is here. This is the fourth. The fifth one is what we generally expect. This is the fifth. And the sixth one is the exponential decay. So this is the sixth. Okay, so just a couple of points based on this plot. So 5 is what is the actual physical solution, close to observation. Because you can see that it is accelerating. Okay. Initially slower value of velocity at r is equal to rc, u becomes equal to cs. And then it accelerates further. It becomes supersonic. This is what you have. Fine. So in case of one, it's not a single valued function. Okay. So it's a double value. Means at one r, double valued at some r. Okay. So this is not physically acceptable. Not physically acceptable. Fine. What about two? Means this one again same double valued function and much away from solar surface. So again not accepted. Third, third is that this one, right? This one is the third. So third one is it is way beyond supersonic. So it is always supersonic, which is not observed actually. Okay, so this is the third. The fourth is which one? This one. Fourth is not supersonic at all, which is also not correct. So it's not acceptable again. The fifth one is the only acceptable solution, is the acceptable solution, which is following whatever we have written. And what is the sixth? Sixth is decaying function. So opposite, opposite to what is observed. So acceptable when C is actually equal to minus. Okay, so these are the explanation of this particular plot. Okay, so so you can see that the Parker's theory of solar acceleration, one of the solutions is perfect. Okay, next is, I think there is a question based on the critical radius, so critical distance. Okay, so critical distance, which is RC, is equal to Gm divided by 2 CSS square. So just remember that Cs, let me see. Right? Okay, I think there is a problem here. Let me just so Cs, what we are writing is that is equal to root RT. Okay, so it will be root. So R can be written as, this is the universal gas constant. So 8.3 into 10 to the power 7 in all UVSI units, and into 10 to the power 6 Kelvin. So what is 10 to the power 6 Kelvin? This is the temperature of the core. Okay. So this is your test temperature, and this is your R, universal gas constant. This comes out to be about 10 to the power 7 centimeter per second, which is 10 to the power 5 meter per second. Okay. So at RC is roughly come out to be 10 R naught, because RC is Gm by 2 CSS square. So M being 3 into 10 to the power 26. All other places, this constants, if you do, so it comes out to be, RC comes out to be 10 times the radius of sun. So RC is about 10 times the radius of sun. Okay, so these are a couple of things. Now, let's talk about a little bit about the space weather and what are the different space weather terms and the sequences of events. Just quickly let us wrap it out, and then we can stop for today. In the next session, we will do completely some numerical type questions based on everything. So this is the space weather. So I just quickly write down certain points. These are all there in the lecture notes. Just read those. Okay. So this space weather, color, the space weather, the changes in space environment that affects the Earth's atmosphere. Earth's atmosphere means upper atmosphere. It's not the lower atmosphere much of the importance, but there are some importances definitely. Okay, so conditions on the sun and solar winds, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-borne or ground-based technologies. Okay, so these are the things. So some terms you can read this we have discussed also. So solar flare. What is that? What is a solar flare? This is nothing but an eruption on the sun that emits X-rays or UV rays and other particles. Okay, this is solar flare. Second is coronal mass ejection. So this is another important thing. So a disturbance, all are related to the solar wind, you can understand. In solar wind caused by eruption. So when there is a peak solar activity, these things happen. Eruption on the sun. Done. Next is the solar wind. Requires no introduction because we are talking about this for a long period of time. It's just outward flow of electrons, protons, and magnetic field from the sun. Fine. The fourth is geomagnetic storm. This is an important thing. So this is the disturbance. So these are all definitions you can see. Disturbance in near Earth particles and magnetic fields. So these are the magnetic fields near the Earth. That's why geomagnetic storms. Okay, magnetic fields that can upset technology and systems like satellite communication and all those things, and also responsible for aurora. So the geomagnetic storms. Next is radiation storm. So a large flux of solar energetic proton. Okay. And the last is the radio blackout. So an enhancement of lower ionosphere as a result of X-ray flares. Okay. So these are couple of space weather events. Okay. So let us quickly write down the sequence of events. So one is the active region on the sun erupts, of course, during the peak solar activity. So how it erupts as the solar flares and high energetic particle, or you have coronal mass ejection. Okay. So these are the couple of things. Yeah. Okay. Energetic particles and the coronal mass. Okay. Second is the X-rays. Based on this, reach Earth in 8 minutes. Speed of sound. Sorry, speed of light. Third, energetic particle. So different. So it reach Earth in 15 minutes to 24 hours. Okay. And the fourth is the coronal mass ejection. It comes in 1 to 4 days. All right. These are the couple of things. And let's talk about a little bit about different weather storms. So these are a couple of things which you have to study and you have to remember. The first one is your radio blackouts. Second is the radiation storm. And the third is the geomagnetic storm. Okay, so radio blackouts. So solar flares. Okay, solar flares send out X-rays. Okay, which reaches which reach the Earth in 8 minutes. So it modifies the ionosphere. Okay, what are the impacts? Impacts are throughout same. With all those events has the same impact. So one is that airline communication gets impacted. Next is high frequency radio waves. So radio operators that gets impacted and satellite communication. Okay, so these are the impacts. What about radiation storms? Solar flares and the coronal mass ejection send out energetic particles which take or which reach the earth within 15 minutes to 24 hours, and it modify the high latitude and the impacts as well. What about geomagnetic storm? The coronal mass ejection is the most important thing. CME send out magnetic clouds within 1 to 4 days, and it accelerate particles within magnetosphere and ionosphere. Here the impact for this is high frequency radio communication, GPS and aurora. Okay, so these are a couple of things. Okay, what else? What else? Yeah, there are some classifications that we will list down and will end today's lecture. Okay, the first one is your solar flares. Okay, so B type is associate X-ray flux with intensity less than 10 to the power minus 6. It has no effect on Earth. Next is C. C type is intensity is now 1 into 10 to the power minus 6 to 1 into 10 to the power minus 5. So this has possible effects on space missions. Next is N. N has 1 to 10 to the power minus 5, 1 into 10 to the power minus 4. This has effect on blackout in radio transmission and possible damages in astronauts outside spacecraft. And finally, we have X, which is intensity of the order 10 to the power minus 4. It damages satellites or satellite communication. Okay, so these are the possible types of solar flares. Similarly, second is geomagnetic storm. So let's list it down. So there were many G1, G2, G3, G4, G5. This is minor, this is moderate, this is strong, this is severe, and this is extreme. Okay, so based on some value is there, KP which is equal to 5 and index to measure. Okay, and this has 900 per 11-year cycle. 11-year cycle because these are the solar cycle. So within one solar cycle, which is 11 years, 900 times this can happen. This is the frequency. Okay, so 360 per cycle. Next is 130. Next is 60. That's 4. Okay, these are the couple of things. Third is solar radiation storm. Radiation storm. Okay, this has now 5 categories again. So these are depending on the energetic particles. So these are 10 square mega electron volt, 10 cube, 10 to the power 4, 10 to the power 5. So this way the intensity increases. Okay, and frequency is what? 50 per cycle. It's 25, 10, 3, and 1. This cycle is the solar cycle we can. Okay, and the fourth one is the radio blackouts. So radio blackouts will be based on the your X-ray intensity. So you have again R1 to R5. Okay, so 10 to the power minus 5, 5 into 10 to the power minus 5, it will be increased, 10 to the power minus 4, further increase to into 10 to the power. And this can happen 2000 per cycle, huge, 350 per cycle, 175 per cycle, 8 per cycle, sometimes it is less than 1 per cycle. So remember this cycle is 11-year solar cycle. Okay, so these are the couple of points about the space meters. Okay. So I have given a full introduction of this. There are many things which I have not discussed here. You can just cover it there from the lecture notes. So yeah, this ends the entire week 12. And in the next session, let me just rename this. So the next session we will be doing uh, your numerical questions. I will try to jot down some 15 to 20 numerical solutions. We will solve those questions step by step, which will be related to all these weeks. And yeah, then I will, then I think that will be enough for uh, this particular course. Okay, fine. So just a quick recap of what we have discussed. So this is the space weather part. Right? Okay. So here we have discussed about the assignment 11 questions, and after that we started with the Parker's theory of solar wind acceleration. We have seen that the hydrostatic approximation is resulting into the deviation from the theory, and it is creating problem. Improvement is made. We have not taken the hydrostatic approximation, and one change I have made, that since the plasma is a single fluid, we are taking Q is equal to n kBt. But in the NPTEL lecture note, it is 2n kBt. So be careful. With 2n kBt, you will never get the expression, final expression, which it should be. So based on n kBt, we have tried. We have found out the critical distance formula, and we have introduced the isothermal speed of sound into that, and we have discussed the cases and the final expressions. We have discussed this plot, and yeah, that's all. And then we headed towards the space weather. Just a very brief introduction and a couple of types of geomagnetic storm, solar flares, solar radiation storm, and radiation storms. Okay, so with this, I think we can stop today, and we will meet on next Tuesday, same time, 6 to 8, and we will discuss the numerical questions and finish the course. Okay, thank you, everyone.